Delicious. Oh, hey, just making some frosting for my turkey. Just probably wondering why I've got all this apron on. Well, we're going to talk about a recipe. That's right, a recipe for solving differential equations. It's going to be lovely. What do I need before I get started? Well, you need a bowl, you need a wooden spoon, you're going to need some algebra, some integration techniques, and then exponential and logarithmic rules. You got all that? Okay, a little dash of salt, and let's keep going. All right, I'm thinking of a function. Okay, here's what I'll tell you. It passes through the point 211, and its derivative at any point can be found by the equation 2x times the quantity 2x squared plus 1. What's the function? Yeah, okay, so I'm a dork, and here's how I would do it, right? It sounds like was plus change equals is, right? I know the rate of change of a function. I know where the function was. I need to be able to figure out where the function is at any x value. So I can basically take the antiderivative of that derivative equation, right? The differential equation. So if f prime is 2x times 2x squared plus 1, I know that that's the same thing as 4x cubed plus 2x. And I can take the antiderivative of that pretty easily, right? That's going to be x to the fourth plus x squared plus some mystery constant. Okay, all I got to figure out is what that mystery constant is. And to do that, I need that initial condition, 211, so I can plug in 211 into the places that they're supposed to go. F of 2 is 2 to the fourth plus 2 squared plus the mystery constant. That's all got to equal 11. And when you flip, flap, floop, add things together, you see that C has to be -9. Gotcha! My function is f of x is x to the fourth plus x squared minus 9. That's the function that passes through 211 and has the right derivative. But, man, that's a big but. What if I change the slope calculation at any point to be 2y? Huh? What if I changed it to 2y times 2x squared plus 1? How would we go then? Could we just integrate 2y times 2x squared plus 1? Would we integrate that with respect to x, with respect to y, with respect to both? Is there some kind of implicit anti-differentiation? No, there's not. We're not going to do that. This is calculus of a single variable. You can do that. You can integrate y with respect to x, and you can integrate x with respect to y, but that's for a future time. So here's how we're going to follow this recipe. All right, it's a recipe. We're going to follow it every single time. I like to cook. Well, let me change that. I like to eat. So I think following recipes is one of the easiest ways to cook things, in my opinion. You ever follow a recipe? You ever follow a recipe so many times that you don't have to look at the recipe? Gosh, I can't even tell you how many times I've made macaroni. I don't even have to look at the box in order to know how to make that macaroni anymore. So the more you follow this recipe, the better and better you're going to get. Oh, nice analogy. Okay. The game-breaking play for this recipe is the very first step. You've got to have the first step here. And without it, you're not going to get the points that are available on the AP exam. I mean, if you're only worried about solving these things for the AP exam, then that's a big worry, is that you're not going to get the points that are available. If you're talking about mathematical purity, you have to have that first step in order to do any of the subsequent steps. Okay, so separation of variables is going to be integral to the solving of differential equations. So here we go. Here is the recipe in all its glory. So first thing you're going to do is separate the variables. It's going to take a little bit of algebra. It's not going to be too tough. Then you're going to integrate both sides of the equation. That's going to take some calculus. Then you're going to evaluate for the mystery constant. And for that, you need the initial condition. Because after we integrate, right, we'll have that plus c. So then we'll solve for that c. And then we'll just need some algebra to isolate y on one side to get our mystery function that we wanted to solve for. So you're going to want to make sure that that mystery function doesn't have any domain issues or some other little things that you might need to think about. You're not going to see that a ton, but it might happen occasionally, especially if you have some square roots in play or things like you're dividing by an x. Just some things to consider if it were to come up. We'll maybe talk about that in class, but this video probably won't get to that. And then the thing you do at the end is you celebrate because you did it, and then it just matches the rest of the steps. Okay, well, let's show you the steps. Step example 1, you got a function fy equals f of x. That's the solution to the differential equation dy dx is 4 times xy. And we have the initial condition that f of 1 is 9. We want to solve for the specific solution to y equals f of x. So to do that, we're first going to separate the variables. So we'll divide by y and multiply by dx. Now we can integrate because you need that little differential dy and dx in order to integrate. We talked about that last big idea. If you need a little refresher, just go watch some videos. So the integral of dy over y and the integral of 4x dx, well, that's the natural log of the absolute value of y, and then 2x squared plus a constant c. Let me just take a little time out. Why didn't I add c to both sides? Well, the reason I didn't do that is because if I add a mystery constant to two sides of the equation, it's essentially like adding one mystery constant to one side of the equation, right? So I don't have to add two different constants, two mystery. That's too much going on. It is the same thing, adding two mystery constants to both sides as it is to add one mystery constant to one side. We'll add it to the side with x, because remember, we're trying to isolate y. So let's keep everything away from y that we can. So then we'll take that natural log of the absolute value of y is equal to 2x squared plus c, sub in our initial condition. So 1 goes in for x, 9 goes in for y. A little bit of algebra later, you got c is equal to the natural log of 9 minus 2. We'll take that, sub it back in to the c that where we left off. To get that, the natural log of the absolute value of y is 2x squared plus the natural log of 9 minus 2. Well, from then, it's just a bunch of algebra, right? So we've just got to exponentiate both sides. That's a way to get rid of natural log. So when you exponentiate both sides, you get the e to the natural log of critter is just the critter, which is the absolute value of y, is equal to e to the 2x squared minus 2 plus the natural log of 9. Now, the way to deal with that is to recognize that when you have a sum in the exponents, it's actually a product of like bases. So that's e to the natural log of 9 times e to the 2x squared minus 2, which is just 9 times e to the 2x squared minus 2. Now, we'll drop those absolute value bars. Drop them like they're hot. And to do that, we need to consider plus or minus 9e to the critter. Now, plus or minus is not a function, so we need to make a judgment call. And the judgment is going to link back to the initial condition. The initial condition 1, 9. When I plug in 1 to x, I've got to get positive 9. And the only way to do that is if I start with a positive 9e to the critter. So now I know the solution to the differential equation that we started with, dy dx, is 4xy, is y equals 9e to the 2x squared minus 2, with 1, 9 being the initial condition. Whew, that was cool. All right, so let me just warn you guys, there's some bogus thinking alert happening here. There's like one step of calculus and there's a lot of algebra here. So where are you going to mess up? With the algebra. Good calculus is ruined by bad algebra. Guys, that is a fact, right? If you think that e to the sum, like e to the a plus b. If you think that is e to the a plus e to the b, stop it. Don't do that. That's incorrect. Don't do that. Instead, remember that e to the a plus b is e to the a times e to the b. You're going to get a lot of these differential equations, solving them with some natural logs. And to get rid of natural logs, you need to exponentiate. You're going to see this a lot. So this is a mistake that is a bogus thinking alert. Don't go there. Make sure you have the right exponential properties and natural log properties in mind. You're going to see them a lot. That's a rookie mistake. Don't do that. All right, let's check out another example. This is from the 2017 BC free response. It's the potato question, talking about baking, talking about cooking, and they're talking about a baked potato. It was a perfect question. But we get that dg dt, right, where g is the temperature of this potato. Dg dt is negative quantity g minus 27 to the 2/3. So we just have to find an expression for g of t, knowing that the initial condition g of 0 is 91. So we're going to do the recipe. We're going to start with the differential equation and separate the variables. So divide by the quantity g minus 27 to the 2/3 and multiply by dt. You see it there in green, the changes that I've made. Then we'll integrate. So integrating those sides. Now I have a chunk raised to the 2/3. Nice little u substitution problem here, I might add. It's not really too tough because the derivative of g minus 27 is 1 times dg, so it's not a very tough u substitution problem. So that's basically like chunk to the negative 2/3. So the antiderivative of chunk to the negative 2/3 would be chunk to the positive 1/3, and then multiply by 3. And then the integral of -1 with respect to t is negative t plus our constant. Now, I'll say another bogus thinking alert is don't forget to add the constant right when you integrate. That constant of integration, oh wait, did I say constant of integration? Yeah, so when you integrate, you need to make sure that you include the plus c. Don't think that you can just add a constant like, oops, I forgot, and then add it at the end. That's not the right place. That's not the path of mathematical righteousness. Add the c now, right when you integrate. Okay, so separate, integrate, I'll evaluate using the initial condition 0, 91. So throw all those things into the right places. 3 times 91 minus 27 to the 1/3 is negative 0 plus c. So c is equal to 12. So we'll take c is equal to 12, sub it back in for the plus c. So we'll pick up where we left off. And 3 times the quantity g minus 27 to the 1/3 is negative t plus 12. And then we'll just algebra our way out of that to get that g is the quantity, negative t over 3 plus 4 cubed plus 27. So I think in that problem, they asked for like, what was the temperature at t equals 3 or something like that. You just had to sub in, and it was pretty simple. I mean, it wasn't that tough. But the big point getter in that problem was that process: separate, integrate, evaluate, isolate. Like there's a lot of points available. I think there's like 4 or 5 points available for a 9-point question, it's a sizable chunk. If that's the only thing you're worried about with learning calculus is what your score in the AP exam is, then you're going to want to take note that this process is pretty important. All right, one more example, and we're going to do this one kind of in a general way. So I'm gonna actually switch around the evaluate and isolate, right? Because that's what I can do when I'm cooking, right? I can sometimes do things in a different order, and it's okay. But sometimes if I do things in a different order, it totally turns into a pile of crap. So I need to make sure that I stay with the separate and integrate. Those are guaranteed. You have to do those in that order, 1 and 2. But you can switch around the last 2. And I'll show you what that looks like. You can get a general solution and then solve for C. So let me show you what that looks like. here with this third example. So if dy dx is 5y minus 5, and the initial condition y of 3 is negative 4, we want to be able to find an expression for y. Find the function that is the solution to this differential equation. So we'll start with the differential equation. We'll actually need to factor that. Not just, I mean, you could divide by 5y minus 5, the chunk, in order to separate the variables. But I like just dividing by y minus 1. Again, if it is algebraically legit, do it. Don't feel like you have to do things exactly the way that I'm setting them out. Again, if it's algebraically legit and there's no mathematical issue with what you're doing, then you can do it. That's okay. So I choose to factor the 5 and divide by y minus 1. So I'll divide by the y minus 1 factor, multiply by dx. You can see the changes in green. So that's my first step, separate. Got it. Now I will integrate. So I'm going to integrate both sides. So the integral is equal to the integral. Not too tough to integrate those two sides. We get the natural log of the absolute value of y minus 1 is equal to 5x plus c. So now, instead of evaluating by plugging in the initial condition 3, negative 4, I'm going to isolate y. All right, so check that out. I'm going to exponentiate both sides. So e to this side, e to that side is going to get me the absolute value of y minus 1, and then e raised to the 5x plus c. Don't rookie mistake that. It's not e to the 5x plus a constant. No, don't do that. It's e to the 5x times e to the c, and e to the c is just another unknown constant. Okay, so e to the c is going to just morph into a new unknown constant c. Then I'm going to drop the absolute values, and if I drop the absolute values, I got to do plus or minus, but plus or minus c is just an unknown constant. So I know that y minus 1 is still c e to the 5x. Add 1, and I have a general solution. All right, so this solution is just a general one for any case where the dy dx might be 5y minus 5. Well, how then do I evaluate for c? Well, now I can plug in the initial condition 3, negative 4. So you can see that happening in red. Plug in those values. I get the value of c is negative 5e to the negative 15th. And then just sub that in place of the c. So y is equal to, you can see that's where the c is supposed to go. So negative 5e to the negative 15th sits in that spot, and then cleaning it up a little bit, combining the exponents. And making it look all pretty, I get that y is equal to 1 minus 5e to the 5x minus 15. And that will satisfy the differential equation. So again, that was kind of switching the last two orders. Instead of evaluating, then isolating, I isolated, then evaluated. Sometimes that's much easier to do than the alternative. And you don't have to do one or the other. You have a little bit of freedom there on the last two steps. So you got yourself some examples there. So as you go forth and start trying to figure out these on your very own, I hope this helps you in that process. Just remember, solving differential equations is as easy as following a recipe, right? There's a lot of symbol pushing around. Okay, there's a lot. I will warn you. I'm going to give it to you straight there. There's a lot of algebra, and there's only one step of calculus. And if you're going to mess up, you're going to mess up with the algebra. That's been the case pretty much all year. You're going to mess up with the algebra or the addition or like subtracting 5 minus 2 and you get 8. And you're like, what? Just silly mistakes like that are a lot of the reasons you're going to get problems incorrect. But you're not going to get problems incorrect, not after this lesson. Double check your final function to make sure that when you plug in the initial condition, you do indeed get what you wanted to. Like, let me do that right now just as a reminder there. This function here, 1 minus 5e to the 5x minus 15. When I plug in 3 for x, I need to get negative 4 out. And does that happen? 5 times 15, 15 minus 15 is 0. E to the 0 is 1. 1 minus 5, yeah, it's negative 4. Okay. Whew. Man, I was going to say, if I mess that up, I'd have to redo this whole video. That will just not be fun. All right. So make sure you double check the initial condition before you abandon the problem. All right. That does it for big idea 4. You've learned how to do a slope field and how to do Euler's method and what the heck logistic growth is. And now you know the coup de grace, how to solve a differential equation using calculus. Now, big idea 5, you're going to need your 3D goggles. So make sure you remember to get some when we return in January. I'll see y'all then. Enjoy. Bye. Yum.